A brief history of our universe. In 1965, two scientists, Arno Penzias and Robert Wilson, were just trying to solve a frustrating problem. They worked at Bell Labs, fine-tuning a massive antenna, but a mysterious static kept interfering with their experiments. They tried everything to get rid of it, tweaking every setting, cleaning every wire, and even clearing out some pigeons nesting in the antenna. But that hum wouldn't go away. Then, it hit them. This wasn't ordinary noise. They had stumbled upon something beyond human comprehension. A faint whisper from the birth of the universe itself, a signal generated nearly 14 billion years ago, traveling across time and space. This was the cosmic microwave background, the oldest light in existence, lingering proof of a cosmic explosion, the Big Bang. In that moment, a quiet mystery was unlocked. This afterglow didn't just reveal the universe's age, it gave us a window into its beginnings, where everything we see, touch, and know began as a single spark. This was our universe's baby picture, a glimpse into an era where galaxies, stars, and planets hadn't yet formed, but their potential was there. With this accidental discovery, Penzias and Wilson opened the door to the ultimate mystery of our existence. Now, let's step through that door together and explore the breathtaking history of our universe. The Big Bang, 13.8 billion years ago. Imagine a point smaller than an atom, containing all the energy, matter, and space of our universe compressed into unimaginable density. This is what scientists believe was the origin of everything, the singularity. Then, in a moment so brief we can barely grasp it, this singularity expanded, an event we now call the Big Bang. But rather than an explosion in space, the Big Bang was an expansion of space itself, a rapid stretching that created time, space, and everything in it. This expansion wasn't calm or quiet. Within an instant, temperatures reached trillions of degrees, and the early universe was a boiling, seething mass of energy. In this moment, the very laws of physics, as we understand them, came into existence. Concepts like gravity, electromagnetism, and the strong and weak nuclear forces began to take shape, giving structure and behavior to this newly born cosmos. And from that small, dense point, the universe began its long journey, expanding outward and cooling down. The early universe, 0 to 10 to the negative 32nd power seconds. The Big Bang set off an unimaginable surge of energy and heat, creating what scientists call a quark-gluon plasma, a thick, chaotic soup made up of the smallest known particles, quarks and gluons. Quarks are the building blocks of protons and neutrons, while gluons act like a kind of glue that binds them together, creating the stable particles that form the atomic nuclei in matter. This state was so dense and energetic that particles couldn't settle or form into anything recognizable. Yet, as the universe continued to expand, it began to cool, and within fractions of a second, quarks and gluons slowed enough to start combining. They merged to form protons and neutrons, which would later make up the cores of atoms. This was an incredibly rapid transformation, taking place in just 1/1,000,000th of a second, but it laid the foundation for the formation of matter as we know it. At this stage, the universe was still a fiery, chaotic place. Temperatures were so high that even the newly formed protons and neutrons couldn't bond permanently with electrons to form stable atoms. But the conditions were set for the next essential phase in our universe's history: formation of basic elements. Just minutes into its life, the universe had cooled enough to allow nuclear fusion to occur. Protons and neutrons, which had been forming in the quark-gluon plasma, now fused together in a process that created the first atomic nuclei. Through this fusion, the universe began producing its first elements, mainly hydrogens and helium, with tiny amounts of lithium. These elements would eventually serve as the raw material for stars and galaxies, but at this stage, they were floating freely as individual nuclei without any electrons attached. Despite this progress, the universe was still a very dark and empty place. This period is often called the Cosmic Dark Age, because while particles existed, there was no light. Photons, particles of light, were present, but they were trapped by free electrons in the plasma that still filled the universe, unable to travel far or illuminate space. The universe had to continue cooling and expanding for hundreds of thousands of years before atoms could form and light could travel freely. During this dark age, the universe was mostly made up of a diffuse, cooling gas of hydrogen and helium stretching out across vast distances. It was the calm before the storm of creativity that would soon follow, the building of stars, galaxies, and all the structures. That would make the cosmos the spectacular place we see today. But these basic elements, simple hydrogen and helium, were essential building blocks. Without them, no stars, no galaxies, and no planets could exist. They would later gather into clouds, condense, and form the very first stars, setting off a chain reaction of creation that would transform the dark universe into one full of light and complexity. This brings us to the next chapters in the universe's history, where the first stars will begin to shine and create the elements that would eventually form everything, from the planets to life itself. The story of the universe was just beginning. Around 380,000 years after the Big Bang, a significant transformation took place in the young universe. Until this point, the universe was filled with a dense, hot plasma of charged particles that trapped light, making it impossible for light to travel freely. However, as the universe expanded and cooled, electrons began to combine with atomic nuclei to form neutral atoms. This process, known as recombination, made the universe transparent to light for the first time, allowing photons to travel across space unimpeded. This first light is what we now detect as our cosmic microwave background. Radiation, a faint afterglow, spread evenly across the universe. Discovered accidentally by Penzias and Wilson in 1965, the CMB offers us a direct view of the universe in its infancy, like an ancient photograph that captures the cosmos just as it was taking shape. Through the CMB, we can observe slight temperature fluctuations, providing insight into the density variations that would later seed galaxies and large cosmic structures. Formation of the first stars and galaxies, approximately 200 million years after the Big Bang. As the universe continued to cool and expand, gravity began to assert its influence over the vast clouds of hydrogen and helium that had formed. Over time, gravitational attraction caused these clouds to collapse inward, creating the conditions necessary for nuclear fusion to ignite. In these stellar nurseries, the first stars were born, lighting up the universe and ending the cosmic dark age. These stars were colossal, burning hotter and faster than most stars we see today. The intense light and energy they emitted began shaping their surroundings, initiating the processes that would lead to the formation of galaxies. These early stars gradually gathered together, their mutual gravitational pulls forming the first proto-galaxies. Over billions of years, these proto-galaxies merged, collided, and evolved into the complex galaxies we observe today, including the Milky Way. With the birth of the first stars and proto-galaxies, the universe entered a phase known as the ionization era. The intense ultraviolet UV radiation from these early stars began to ionize the surrounding hydrogen gas, stripping electrons from their atoms and making the universe more transparent to light once again. This process of reionization marked the true end of the cosmic dark age, as it allowed starlight to travel freely through space, illuminating the growing cosmic landscape. During this period, galaxies began to form more complex structures and exerted influence over larger regions. The reionization process shaped the structure of the universe, clearing paths through which light could travel, and laid the foundation for the intricate web of galaxies, stars, and cosmic structures that would follow. As more stars formed and evolved, galaxies began to group together under the influence of gravity. Over time, these galaxies merged into larger structures, forming clusters, and eventually superclusters, vast groupings of galaxies that stretch across hundreds of millions of light years. This web of clusters and superclusters became the backbone of the cosmic structure, with galaxies strung along vast filaments of dark matter. Inside galaxies, star formation continued, with stars undergoing life cycles that led to the creation of heavier elements, like carbon, oxygen, and iron in their cores. When massive stars ended their lives in powerful supernovae explosions, these elements were scattered into space, enriching nearby clouds of gas and dust. These heavier elements would eventually become the building blocks for planets, complex chemistry, and ultimately, life. The universe had now grown into a vast, complex, and interconnected network of galaxies and stars, setting the stage for the emergence of solar systems, and, much later, the conditions necessary for life. In this grand process of cosmic evolution, the elements that make up our world and our bodies were forged in the hearts of ancient stars and spread across the universe, ready to be part of the next chapters of cosmic history. The story of our solar system begins about 4.6 billion years ago, with a sprawling cloud of gas and dust known as the solar nebula. Gravity took center stage, pulling this molecular cloud inward until it collapsed under its own weight. At the core, pressure and heat ignited nuclear fusion, sparking the birth of our sun. Leftover particles whirled around it, forming a flat, rotating disk. Over millions of years, these particles coalesced, eventually becoming planets, moons, and smaller bodies that now populate our solar system. Earth itself emerged from this cosmic construction, growing gradually as tiny bits of dust and gas stuck together layer by layer. About 3.8 billion years ago, Earth's journey took a revolutionary turn with the emergence of life. In a planet swarming with chemical reactions, the first forms of life, a microscopic band of single-celled organisms, appeared. These early life forms were remarkable for their simplicity, but equally so for their resilience. Over time, some evolved the ability to harness sunlight through photosynthesis, releasing oxygen as a byproduct. This oxygen began to accumulate, dramatically altering Earth's atmosphere and paving the way for complex life forms that could thrive in oxygen-rich environments. Fast forward to around 541 million years ago, and Earth witnessed the Cambrian explosion, an unprecedented burst in biological diversity. Species with complex body structures like exoskeletons and complex eyes appeared, opening new ways to survive, hunt, and explore. The diversity of life increased, but so did catastrophic events that tested Earth's inhabitants. Mass extinctions, including the Permian-Triassic and Cretaceous-Paleogene events, wiped out vast numbers of species, but also shaped the course of evolution, making room for new life forms to rise. In the relatively recent timeline, around 2 million years ago, the human story began, with Homo sapiens emerging as an intelligent, adaptable species that would go on to dominate Earth. As we look to the present, the cosmos continues to reveal its mysteries. Scientists have found that the universe's expansion is accelerating, driven by a force called dark energy. This discovery opens questions about the future of our universe. Will it end in a big freeze as galaxies drift into eternal isolation? Or will it collapse in a fiery big crunch, or perhaps tear apart in a big rip? While we don't yet have all the answers, each discovery adds a piece to the puzzle of our cosmic history, urging us to explore, question, and imagine what's still left to uncover in the grand expanse of the universe.